There are numerous ways to try to unlock the mysteries of aging. You could study long-lived individuals like centenarians and supercentenarians, particularly long-lived smokers, perhaps, to uncover the secrets to their resilience. Or you could go in the opposite direction and study short-lived people, tragic, accelerated aging syndromes like progeria, where children age at 8 to 10 times the normal rate, wrinkling, balding, and then typically dying around age 13 of a heart attack or stroke. Or you could study long-lived animals. There are mammals, such as the bowhead whale, that can live hundreds of years. There are oysters and clams whose hearts can beat over 1 billion times over its 5-century lifespan. What accounts for the 10,000-fold range of lifespan in the animal kingdom? Most of the aging pathways identified as the hallmarks of aging were established using so-called model organisms, such as yeast, worms, flies, and mice, simpler species that may nonetheless offer insights due to the remarkable conservation of common aging mechanisms through the eons of evolutionary time. Aging used to be considered simply too complex to study, a constellation of internal and external influences too complicated to disentangle. But then, the game changer, the discovery that a single gene mutation could dramatically prolong the lifespan and youthful state of a tiny worm known as C. elegans. C. elegans has since wormed its way deep into the study of longevity. It seems we shared a common ancestor about 500 million years ago, and to this day we still share about half their genes. With a lifespan of only 2 to 3 weeks, their fast turnover allows researchers to rapidly assess the effects of genetic or dietary tweaks, unlike humans, who are described as not an easy-to-study system, both for ethical as well as for practical reasons. Even simpler, the single-celled organism Saccharomyces cerevisiae, otherwise known as brewer's or baker's yeast, in 1959 it was discovered that yeast cells are not immortal, dividing only a finite number of times. They are even more evolutionarily divergent, though. We haven't shared a common ancestor with brewer's yeast for more than 1 billion years, and only have about 30% of their genes in common at this point, but their microscopic size and even faster turnover allows for high-throughput systems able to screen through more than 1,000 different compounds a day for potentially lifespan-extending properties. And even if those yeast longevity compounds fail to translate to extending human life, yeast researchers argue they could still be useful for brewing extra beer. Yeast have a lifespan that can be measured in days, worms in weeks, fruit flies, another common model, in months, compared to mice that can live for years. But mice and men were one as few as 75 million years ago, arising in the mammalian explosion short after the resolution of the asteroid v. dinosaurs matchup. Mice share about 85% of their genes with humans. Granted, it's an important 15%. Humans are not just more complex anatomically than rodents, but more complex even on a cellular level. Extrapolating data from lab animals is infamously fraught with difficulty. Fewer than 1 in 10 cancer drugs that seem to work in mice even make it into human clinical trials, and hundreds of seemingly promising Alzheimer's drugs have similarly been lost in translation. As one review in the journal Trends in Biotechnology put it, humans are not huge worms or big mice. We are, however, big primates. Rhesus monkeys are also used in aging research, though can live up to 40 years, stretching research timelines. Their DNA is 93% identical to humans, though as similarity increases, so too do ethical concerns regarding experimentation. One might expect research on dogs to perhaps be most sensitive, but there are citizen science initiatives in which family dogs are enrolled in non-invasive studies to study, for example, the genetics of why some so-called Methuselah dogs reach ages of 25 or more, but 99.9% of other dogs do not. For example, mixed-breed dogs live more than a year longer than the same-sized purebred dogs, who can be plagued with certain genetic disorders. Aged pooches suffer many of the same ravages of aging: arthritis, cancer, cataracts, kidney problems, muscle loss, etc. Advances in canine longevity might not only be applicable to human aging, but have the intrinsic value of enhancing the quality and quantity of life of the more than 70 million companions we share our homes with in the U.S. alone.